Hello people, I'm Phil and welcome back to my series on building a virtual machine from scratch. Last time we went on a programming spree and developed an entire minimal virtual machine in about a half hour. And this time what we're going to do is add some features to it and look at beginning to build an assembler for our virtual machine. So I'm in my workspace, which is the same as we left it last time. And what we're going to do is we're going to open up our stack VM CPP file. And we're going to go down here and we're going to add some more instructions. So we're going to add, let's see, what did we have before? So we're gonna add actually a case statement for 2, and this is going to be subtraction. We'll break. We'll have case 3 for multiplication, case 4 for division, and we'll stick with those for now. And what we'll do for each of these cases is, since we have no screen, we'll print to the standard out for right now. We'll subtract and show our memory at that spot. And then we can actually perform our subtraction. And then we will decrement our stack pointer. Then let's do the same thing for multiplication and division. And in fact, let's yank that and put it there. And we'll do multiplication. And let's do the same thing for division. We'll divide these two numbers. Now remember, we have only integers, so when we do division it will actually be integer division, not floating point division. So that gives us addition, subtraction, a multiplication, division, and a halt instruction. So now that we've added some features, let's try them out. Let's go to our main CPP file and add or expand our program. So right now we're pushing 3 to the stack, 4 to the stack, then we're adding them. So let's push another number onto the stack. Let's push 5, and let's perform another instruction. Let's see how many we're supposed to have here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6 zeros. So we'll have 1, 2, 3, 4, 5, 6, and 1 is add. So let's subtract 5. So we'll do a 2, and then let's multiply by 3. So we'll do a multiplication operation. So 0x 4, 1, 2, 3, 4, 5, 6. And we will divide by 2. Let's see. and then at the end we'll halt. I think we have everything covered. So let's try this out. Let's compile our program, and now we have our stack VM. If we run it, let's see, I didn't even do this beforehand, so let's see what happens. Our top of the stack is 3, 4, then we add 3 and 4 and get 7, then we push 5 to the stack, and we subtract 5 from 7 and get 2. We push 3 to the stack, we multiply 2 and 3 and get 6. Push 2 to the stack, divide 6 by 2, and get 3. And then we halt with the top of the stack being 3. So that actually worked correctly the first time. Pretty awesome. Now, let's go back to our main program where we're testing this thing out. Now, if you notice, it's a bit tedious to write your program like this. You have to remember your instructions, the hexadecimal values of the instructions, and it just so happens that our instructions for our numbers can be written as normal integers because of how we define our instructions, but you could write these as hexadecimal values as well. And it's quite tedious to create programs this way. And believe it or not, in the past, when computers were brand new, people coded like this for years. They created machine instructions by hand and fed them into the computer. Some years later, something called assembly language was created, which allowed people to say things like, which allowed people to say something like, I want to push 3 to the stack, then I want to push 4 to the stack, and then I want to add things together. And so instead of having to remember hexadecimal values for push and add and subtract and so forth, they had words that were easy to remember, or mnemonics. And so that's what we want to be able to do with our virtual machine. We don't want to have to create these vectors of hexadecimal values and have to remember every single instruction that we have, because we're going to have more than just addition, subtraction, multiplication, and division. We're going to have lots of instructions, and we don't want to have to remember these values. So what we're going to do is create our own assembly language. And to do that, we need to create an assembler. So what we're going to do is make clean and clear our things out. We're going to start creating our own assembler, and to do that we should organize our files. So let's make some directories. We're going to create a directory for our virtual machine and call it stack VM, and then we're also going to create a directory for our assembler, and I'm going to call it SASM because I want to, since our virtual machine is stack based, it will be a stack machine assembler. So we'll create those directories, and now we'll move our files. We can move our files into the stack VM. Let's see, let's move our make file into stack VM. We'll move our stack VM.cpp file into the stack VM directory, and finally move our stack VM.h file into the stack VM directory. So now we have our project organized according to directories. So we have our stack virtual machine, and now we have our directory for our stack assembler. So let's go into our stack assembler directory. It's empty right now, and what we're going to do is we want to be able to read in source files that we create, just like you would for any other assembly language. You want to be able to read in a source file and compile it into binary or machine code. So one of the first things that we have to do to be able to compile something into machine code is we have to read in a string from our source file and break it up into tokens. And that action is called lexing. So we're going to actually break our string up into lexemes. And so the first thing that we're going to do to build our assembler is to create a Lexer. So we'll create, let's go ahead and do that. Let's start out with our header file and create lexer.h. We have our blank file, and we'll let's do some housekeeping. If in def, we'll create lexer h, and then we'll define. Whoops. There we go. Define lexer h, and then we'll end our if here. And now we can use some include statements. We'll have IOStream because we're going to be printing some things out, and we're also going to include vector, the ever useful vector. And now we'll have some type declarations. Let's do some type defs. Let's do a type def. We're going to create a byte. Actually, I always forget if the type defs which direction they go. So let's go into our stack VM and look at our stack VM H file. Type def has the type first and then the definition second. Okay. Just wanted to make sure that we weren't going to have any errors. Let's go back into SASM and open up our Lexer. Now, let's add another type def, and it'll be standard vector, standard strings. We're going to have a vector of strings, and we're going to call that strings. Now, what we'll do is we'll create an enum and state, and it's going to be of type byte. And what we're going to do is create an enumeration of states. Now, maybe I should explain a little bit. Our Lexer, the way that it's going to work is it's going to be a simple finite state machine. And finite state machines are great for doing things like lexing. And so you'll be able to see one in a second. For right now, we're going to create some states for a finite state machine. And we're going to have a start state, a read char state, a read block state, skip, dump, comment, and end. That takes care of our states for a finite state machine. Now let's create a class for our Lexer called Lexer. And let's create some private functions. We'll create one called myIsSpace. That will take a char. We'll do isSpecial, which will take a char. We'll create something called isGroup, which will take a char, and we'll also have some an end char and beginning char, which we're going to use for our groups. Then we'll create some public methods we'll have something called strings and a function called lex, which will take in a string s. And that's it for the header of our Lexer. So let's go ahead and create our Lexer CPP file. And it will need to include lexer.h. Let me take a look at my notes because this is a bigger program. So it will take lexer.h, and let's just start out by defining our strings function. Actually, our lex function, which will output a vector of strings. And it will start out with creating a variable, our string list, which is what we're going to return at the end of our function. So let's go ahead and do that. Let's return our string list. Then we'll need a few other things. We need a buffer, so let's create a lexeme buffer. So our lexemes will have a maximum size of 256. We're going to create some other counters. We're going to have an I, which is 0, J, 0. We're going to our Lexer is going to have a state called state, and we're going to begin in the start state. We're going to have a variable called done, which will be 0, and we're going to get the length of our string, and we're also going to have a balance variable. This balance variable will actually be to match things like parentheses. It will help us match things. So what we'll do is our finite state machine will go in a loop. So while I is less than length, we're going to switch our state, or perform a switch on our state, and we're going to have cases. So we're going to have start, break, case, read char, break, case, read block, break, we're also going to do, let's see, what are our other states? We're going to do skip, we're going to do dump, this should be a colon. We're going to do comment. Comment is actually a way for us to ignore comments in our assembly language code. So we're going to be able to write comments. And then finally we'll have end. Okay, so that's an outline of our lex function. Let's go up here, and for start, what we'll do is, if something is a space, then what we're going to do is skip it, because we will not care about spaces. Else if it's a group, is group. There we go. If something is a group, then we'll check if the first character is a double quote. If it is, then we will add to our lexeme, add that character to our lexeme, add to our J, add to I, and then we'll move to state, read block. All right, else if our first character is a comment or is a /, and our second character is a /. Actually, this is I plus 1. I probably should do that. Then we have a comment. So we're gonna add 2 to I and change the state of our finite state machine to comment, and it will go and read a comment. Else, what we'll do is change our state to read char. All right, and that takes care of the start state. Now in the read char state, what we're going to do is check if our character is a space. Whoops. And if it is, we will go to the dump state. Otherwise, if our first character is a \, then what we want to do is skip over that character for now. We'll change this later. Else if is group. Then what we want to do is check if the first character is a quote. And if it is, we'll add to our lexeme and we'll increment J, increment I, and change our state to read block. Else if our first character, or actually, let's see, if it is special. We have certain special characters in our assembly language. So if the character is special and J equals 0, then our lexeme buffer will add to it, and we'll do J. We'll increment J, increment I, and then we will change our state to read to dump, actually. And then else if first character equals a // and first character +1. We'll keep spaces in there for now. Equals a // then we'll add 2 to I and change our state to comment. Else we add to our lexeme, add a character, increment j, increment I, and that is our read char block. So now let's do our read block. And if our first character is a beginning character and our first character does not equal a quote, then what we're going to do is increment our balance and add that character to our lexeme, increment j, increment I, and that is let's see, otherwise let's do else if our first character is an end character, then we decrement balance. And also lexeme, we'll add that character to our lexeme, increment j, increment I, and if the balance is less than or equal to 0, we'll change our state to dump. Okay. Else, if end char is a double quote and our character equals a backslash, we will actually increment, we're going to ignore it for right now. And actually, let's put a to do in here. We don't want this to get too huge. Fix this to actually record the chars. All right. Now, else if. Actually, all we have left is an else. So let's do that. Else, we'll record our character in our lexeme. We'll increment j, increment I, and that's it for read block. So now we'll do skip. So if my is space for the character, whoops, then we'll increment I, else, we'll change the state to read char. And that's it for skip. Now we'll do dump. Dump is if j is less than 0, then we'll add the null terminator to our lexeme, and we'll add push back. We're going to add our lexeme to our string list, and then we're going to set j to 0. Then what we want to do is set our state to start, and that's it for dump. Now we have to deal with comment. So if our first character does not equal a new line character, then we will increment, basically ignoring the comment. Else, we'll change our state to read char. Skip the comment. Now the only thing we have left is the end state. So when it's the end, I equals length, and that's it. So then we'll go down here, and before we return our list, we're going to check if j is greater than 0, and if it is, we're going to record. We're actually going to set the null terminator for our lexeme and do a string list, push back lexeme, and that's it for our lex function. All right, so I think we've reached a good stopping point. We've created our lex function for our lexer. Next time what we're going to do is add the other functions that we defined in lexer.h. We're going to go ahead and we're going to create our isSpace, isSpecial, isGroup functions, and we will actually have a working lexer for our assembler. Thanks for watching. Till next time.